So first of all, what is bioimage analysis? Bioimage analysis is a field that is being, let's say, renamed or redefined every few years. We used to call it biomedical image processing, bioimaging. For a while it was called, I think, bioimage informatics. There's still some journals that are called bioimage informatics. And now it kind of converged into this definition and this name, bioimage analysis, no? Which is understood as the field where we automatically extract biophysically meaningful information from images that we have extracted or acquired with the microscope of biological samples. And I like this definition that was done by a friend and a colleague, Christian, from this network of European bioimage analysts, because it also reflects how you can approach the field from different perspectives. No, you could be life scientist or a biophysicist willing to model some biological systems or to do some quantification on your images. You can be someone working on a microscopy facility and still need to have this type of approaches or methods, or someone like me, a simple engineer that are more interested on the automatic part, on creating what we call computer vision or image processing methods that allow us to do this meaningful extraction of information. And then we jump into the big field of machine learning, which is something that is now a very common topic. We hear it even nowadays a lot in the media, but it's actually not so easy to define. So I usually, in my computer vision class, I put this slide to my students, where I tell them that they should think of it as with a historical perspective, let's say. So we know that thanks to technology, well, over centuries, we've been able to automate tasks that have been, for humans, quite tedious, no? That require significant amount of, especially manual and repetitive work. But now, we not only have technology, but we have also a combination with big data. And this allows us to create methods that automate tasks that require what we could call a certain degree of intelligence. No? And this is something a little bit controversial or philosophical, but this is how we jump into the field of artificial intelligence. So what kind of task I'm talking about here? Well, let's say, to simplify, there are tasks that are easy for humans and difficult for machines. For example, until recently, something like face recognition. No? For us, if you think about it, we wake up every day and we mostly, all of us, identify immediately the people in our surrounding. But if you think about it, it's quite challenging because the face of a person changes a lot based on the position, the illumination, if I go from one part to another in the room, if I change my haircut, have glasses or not, etc. So until recently, it was a very difficult task for machines as well. And then there is the other type of task, the ones that are actually quite hard for humans, because they usually involve working with a lot of data. And we are not that good at that. Even face recognition, if it's not the same to recognize the dozens of people that we see almost every day, but if we want to do the same for the millions of faces that may be available in Google or Facebook databases. So what we call machine learning or pattern recognition, data mining is also something that we've been renaming for a while, are all these methods, techniques that have achieved great results, amazing results lately, that they also appear in the media nowadays, that make what we call intelligent systems, well, a very important part, not only of research in many different fields, but also on business models. No? To have the label of machine learning on your resume is almost a must nowadays. But don't get me wrong, machine learning is nothing new. It was already defined by Arthur Samuel at the end of the 50s as the subfield of computer science that gives computers the ability to learn without being explicitly programmed to do so. So what does it mean, this grand definition? Actually, something quite simple. Let's imagine that we have some data points, okay, that we can represent like this. And the target of machine learning is to categorize those points. No? For those objects, we want to indicate what we call their class. For biologists, I always say, I think that we have two types of cells, our red cells, our green cells, and then we want to identify them somehow automatically with the computer. And this representation is actually something that we use, not in 2D, but in a more multidimensional fashion, where we represent every object or every sample, we call it, of our data set based on some measurements. For example, coming back to the example of the cells, we can maybe measure the area of each of the cells in our plate, and maybe the average intensity of all of them. And we can represent them like this. Okay, so this is what we call features. Those measurements is what we call features. And based on these definitions, we have mostly, because there's also things in between, two types of learning, what we call supervised learning, where we start from a data set from which we know the labels. We know which cells are green, which cells are red. Or the unsupervised learning framework, where we just have the data points in the space, but we don't know the categories. But at the end of the day, the target is the same. If we get a new sample in the supervised framework, we want to assign it to one of the two classes that we know. We want to decide if this is a green cell or a red cell. Or in the unsupervised framework, we want to decide, well, maybe if it goes to this cloud of points or to this other cloud of points. So summarizing, we have supervised learning, where the data is labeled, and the target is to build a so-called model or a classifier to automatically label unseen data, no? In a process that we'll see that we call training. If the labels are not discrete, they're not categories, then we're doing regression. No? For example, if we have manual digit, let's say a manual digit problem, no? We have digits that we need to recognize automatically if they belong to one of the 10 categories that are possible, from 0 to 9. No? So we have 10 specific categories. So this is classification. We have 10 classes, and our problem is to assign one of these 10 classes to every sample. If we get a problem of age estimation out of a facial image, no, we pass to our model an image like this, and then it comes back with a number that is a real number, so the positive real number. So we are in the regression framework. In the unsupervised learning, the data comes without labels. Okay, so the target is to somehow model the data to discover those groups, or we call clusters. So this is a typical problem of clustering, right, that you probably hear about or use it even before. So a few concepts. Then we have our samples that are represented by this set of measurements that we call a feature vector, because we put them on a vector. And those values can actually be numerical, but they can also be qualitative. No? Classic problems in machine learning were maybe the classification of medical patients. And then there you would have a combination of numerical values, but also maybe their race, their country of origin, etc. And there are models that can deal with that. In the supervised learning framework, the set of classes is usually known and predefined. So if we're doing digit classification, we know that we have 10 digits and not more or less. Okay? And hopefully, all the samples that belong to the same class, they are similar to each other and dissimilar to the others. Well, in the digit case, it depends on how badly you write. No, maybe the 3 of the 7, they actually look basically the same comparing the writing of 2 people. The most classic problem is binary classification. No? For example, if I have images of biopsies, I want to classify the tissue as tumorous or non-tumorous. We have 2 classes, so it's a binary classification problem. And then there is the concept of the data set, which is just the list of feature vectors with their class, if we are in the supervised framework. If we are in the unsupervised framework, we only have the feature vectors without any class, and we have to discover the groups there. Okay, so what we call a classifier is actually a function, say f, that depends on some parameters, theta, that maps the feature vectors into their classes. Okay? Actually, it's very common that these classifiers, they have 2 steps. One, that we apply them and then provide what we call a sub-decision. Maybe they give us the probability of belonging to each of the classes, no? The probability of being a 0, 1, or 2, or 3, etc. And then a hard decision where we say, no, this is definitely a 3. Maybe we apply a threshold, or typically we take the class with the highest probability. So training, what we call training, is just adjusting those parameters by minimizing the error made by the function. So we typically have what we call a cost, an error or a loss function that we want to minimize. Okay? And once we have that, how do we evaluate and compare them? Well, very simple, no? And now we are all very used to see this kind of concepts, like we just go and count the number of mistakes or hits made by our classifier. No, this is typical. For example, in the COVID test, no, we know that all now are very familiar with true positives, true negatives, false positives, false negatives. So we have a set of samples that we pass through our model, we get the predictions, and then we compare with the real classes, because again, this is supervised, so we know the real class, and then we just count how many we did correctly and how many incorrectly. Okay. And based on this, then in the literature, you find tons of metrics, right? The most simple ones, where you just count how many mistakes you made, no? This is the error rate, or how many hits you made, no? The accuracy. But this is usually sensitive to the number of samples that you have of each class. No? Imagine that the typical example is detection of fraud in banks. No? Like you have transactions, and maybe only 0.001% of those transactions are fraudulent. So you just classify everything as non-fraudulent. You have a 99.999% of accuracy, but it's relative to the error that we have mistake is huge, right? So we usually count more or used to apply other type of metrics like the recall or the true positive rate and the precision, or a combination of both, like the F-score. Okay, this is for classification. Okay, one other decision that we had to take is, now we have our data set, we know how to, let's say, apply classifiers and compare them, but what do we do with all our data points? That was supposed to go later. Okay, so we may be tempted, if we want to model this distribution of points, to use all of them for calculating the parameters of our model. But then we can easily run into a problem of overfitting, no? Where we adjust too much those parameters to the training points, and then any new sample that should be in the distribution is considered as an outsider. So to prevent that, we usually do a partitioning of our data into what we call the training set, typically 2/3 of the data or 80% of the data that we're going to use for training, and then the rest for testing. So we set them apart, and we're never going to use those samples for adjusting the parameters. This is very important. So they're going to be unseen data for the model. And then in some of the models that are used in machine learning, especially artificial neural networks, and what we use in deep learning, we need a special subset of the training set that we call validation, which is a simulation of the test set, okay, inside the training set, to decide when to stop training the algorithm. Some methods are more deterministic. You apply them, you use all the data, and they give you a result. As we will see, training a neural network is an iterative process, and you have to decide when is a good time to stop. And to do that, we check the performance using some of the metrics that we've seen before in the validation set. And if the performance is going down in that simulated test set, or it's actually not improving, then you stop the adjusting of the parameters. An alternative is to do what we call cross-validation. More specifically, k-fold cross-validation. You take all your training data and create k-folds, usually k is 5 or 10. And then you're going to repeat this k times, where you take one fold for testing and the rest for training. Okay, and then you adjust your parameters or find the best parameters based on this cross-validation scheme. And then once you, in a real scenario, once you have the best parameters, you just take all the data, the training data, and use those parameters to train the model and then apply it to the test data. A very particular case when we don't have much data is a leave one out scheme, where you just use folds of one sample, and then you leave, for example, you are classifying videos and you have 10 videos, but you leave one out, and then you repeat this 10 times. Okay, so how do we work on with the microscopy images with this? Actually, before deep learning, a typical approach could be something like this. No, we take our biological samples, we put them in the microscope, and then we take the images from the microscope and we pre-process them, meaning that usually we set them to the same size, resolution, more or less normalize the intensities, etc. And then apply feature extraction. We take those measurements that we mentioned before with a predefined set of measurements that we decided. So we can represent each of those images with a feature vector. Okay, and now we know, hopefully we are in the supervised framework, we know the categories, so we pass those to the model. Actually, before, we usually used to apply feature selection because some of the features were redundant or correlated to each other or non-informative at all, and then we could remove them and then make the whole process much faster. Then we go to the machine learning literature and select one model that, well, it's now fashionable, or we know that it works for that type of data. And then based on the partitioning that we have done, we do the training and the test and check if the result is valid. And this is a big question, no? How do you know if you can be happy with your results? Usually what I tell biologists is to, okay, take the data that they have, or at least part of it, and then give it to some human experts, hopefully more than one. So we can check the error made by the human experts among themselves. And if the error of among humans is similar to the error made by the model, we'll be quite happy about it. Sometimes we can even get better. If it is not that good, then we have to revisit some of these steps and keep working and modifying our models. This is actually where we spend most of the time. Actually, even now in pre-processing the data as well. If the result is valid, then it's great, because then we can go back to the real world, take more images, do exactly the same pre-processing and feature extraction, and reuse the model that was trained. Now we don't have to train it, and then just apply it, okay, in a kind of a production chain. So that's, keep in mind that this is all pre-deep learning. Okay? So for example, I developed a software to do this, to classify pixels a few years back. No? We have images from, in this case, electron microscope. And to create those measurements, those features, what we used to do is to apply a set of filters, predefined filters that enhance some characteristics of the images, like borders, textures, blobs, anything that I had in mind. And you could throw there any kind of filter that you knew. And then we created this software that was interactive. So this is actually called interactive learning approach. So the users could gradually and sparsely introduce some samples of each of the classes that we wanted to have. In this case, in blue, they mark some mitochondria. In red, the membranes of the neurons, and in green, the rest of pixels. And then, in this method, we would take every pixel that was marked by the user, and then represent it by the pixel value and in that position in the input image, but also the pixel values in all these image features. Okay, so we get a long feature vector plus the class, because we know it since the user is giving us feedback. And then we could use any kind of classifier from the literature. Actually, this is all open source, so we took a library that was the state of the art at the moment, and allow the users to use any kind of classifier. Again, this is all pre-deep learning. And then once it is trained, we can classify the rest of pixels in the image by using that learn classifier. Okay, and then we call a semantic segmentation of the image. Every pixel is categorized as belonging to one of these three classes. What kind of classifiers can we use there? Actually, before deep learning, the ones that were more used, and actually they're still very useful, your problem doesn't require as much power, let's say, as deep learning. Well, the most popular ones were SVMs, support vector machines, or those based on trees, random forests and decision trees. There were also artificial neural networks, but they actually were slower to train. At the end of the day, they're just different approaches to separate your data points in feature space either linearly or non-linearly. Okay, so some of them could be faster, some of them could be slower, but at the end of the day, if you want to try something fast, you can use this type of classifiers. So what about deep learning? To jump into deep learning, we have to go a little bit or a lot back in time, back to the 50s, where they introduced at the end of the 50s the first artificial neuron called the perceptron from Rosenblatt, which is actually a very simple linear classifier. Okay, so defined like this. So it's a function that applies some matrix of weights to the feature vector plus a bias. Basically, with W and this scalar, the bias, you are defining this line in feature space. So if by applying this you get a positive value, then you assign it to the positive class. Otherwise, you assign it to the negative class, 0 or minus. Okay, so quite simple, but it was actually a big revolution at the time because it came with a method to iteratively train the model. So we could basically start with random weights, random values for that matrix, and then apply it to one sample. And if the sample was correctly classified, we don't touch the weight because it's doing a good job. And if it's incorrectly classified, then we adjust the weights by the error committed by the classifier. So by doing this, at the end of the day, we're just modifying the line to separate our data points. So basically, it stops when it finds a linear separation of all your data points, but moreover, it only converges if and only if the examples are linearly separable, which could be a problem because in some cases we have scenarios like this. No, this is what we call in computer science an XOR problem. We need two lines. Okay, so they said, okay, well we can stack some neurons. No, like here, this is the input, well, the feature vector of 2. Okay, and each of those nodes, no, these balls here, represent one of these W's and biases. So each of them calculate one line, and then we add another one where we combine them. Okay, so this is what we call one hidden layer because it's in between the input layer and the output layer. And actually, mathematically, they prove that if we use two hidden layers, so we stack one more set of nodes over here, we can solve any problem in classification or regression. Okay, so this is great, right? Problem solved. Well, not that fast because there was a very big issue there. That is that there was no algorithm to train such a nonlinear machine based on iteratively providing more samples. Okay, so this actually led what it is known as the first winter of neural networks at the end of the 60s, and then it moved artificial intelligence towards other type of system, like symbolic system, that actually became the first winter of artificial intelligence in general. They thought it was a dead end. Everything changed in the middle of the 80s with the appearance of this book, or this amazing title, Parallel Distributed Processing Explorations in the Microstructure of Cognition, Psychological and Biological Models. Okay, the one important thing is that Jeff Hinton, which is one of the, let's say, popes of deep learning nowadays, it was already among them. And the big thing on this publication is that it moved artificial intelligence toward optimization. So basically, learning became an error minimization problem. Okay, so they propose an algorithm to train this model iteratively by optimizing suitable error function. So these stack perceptrons that we call multi-layer perceptrons were finally trainable. How do they look? Something like this. We have an input layer, which is just the feature vector. So every of these balls here, they will have one of those measurements, one of those features. And then we have inside one or more hidden layers. Okay, and then in every of those connections, we have the weights. Okay, and in every node, we have the scalar, the bias. So if we want to calculate the value here, we have to sum up the multiplication of all the weights through all these connections, plus the bias. And actually, inspired in biology, but also because it was very convenient mathematically, they included an activation function. So basically, they say a neuron only fires if it reaches some point. No, actually, they use activation functions to reduce the range of the output, because otherwise you keep adding and multiplying, then you can get immensely huge values, which is very hard to optimize. And the algorithm that they use to train this is called backpropagation, because using the chain rule and the error function that we're using, an error function, for example, if you think about the problem of age estimation, could be the mean square error between the predicted age and the actual age, no? For example. So you can, by doing backpropagate the error to each of those weights and see how much they contributed to the error. So you can correct them accordingly. Okay. So you keep showing samples, calculating the error committed, and then go back and adjusting the weights. Okay. So this went on very strongly until the end of the 90s, where relevant contributions decreased. There were competitors that were actually faster, like I said, SVM, random forest, and this was the second winter of neural networks. Okay? And there was a very big problem. That was that when we wanted to include more hidden layers, and this is what we jump into what we call deep learning. Deep learning officially is just including 3 or more layers in between the input and the output layer. Well, there was a problem of what we call the vanishing gradient. No? To calculate the error made by each of those weights, we had to backpropagate the derivative of the error, and from the output towards the input. And by doing that, at the end, if we have 3 or more layers, the gradient starts to be 0. And if it is 0, then we cannot calculate the contribution to the error. So stacking more layers is useless. Okay. And why was this interesting? Because to attack larger problems with larger data, we needed deeper networks. Okay. So how do we jump into the golden era of deep nets? That is where we are right now. Well, everything changed at the end of the 2000s with the 2 approaches, one from that guy that I mentioned before, Hinton, and one from Benjo, to pre-train the models before and then use regular backpropagation later. Okay, so suddenly the floodgates open. We could start using large networks with huge number of weights and new types of layers, initialization, activations, etc. And the most important thing is that there were very important breakthroughs in important fields, at least in machine learning, in computer vision, in natural language processing. And they were also reflected in our daily lives. No? Like we have, for example, the people say how well Google Translate is working nowadays. No? From a few years back to this, well, from the 2000s to this, they improve a lot thanks to these kind of approaches. What people mark as the starting of the revolution, it was 2012, because it was when a model that is called convolutional neural network, okay, from the group from Hinton, they won the ImageNet challenge. This is an annual competition where people have to classify millions of images of thousands of categories. Okay, and until then they use more classic or deterministic methods, and with this approach, they broke the record by a large margin, and then everybody in the field moved toward deep nets. 2013, Google hired this guy. 2014, Facebook hired Jan LeCun, that was the father of the first convolutional network. And in 2018, this trio, Hinton, LeCun, and Benjo, they won the Turing Award. Actually, 2 of them, I think, were awarded the Príncipe de Asturias last year, proposed by Pedro. So 2 important concepts in order to understand these nets, especially those applied to images, are convolutional layers and pooling transformations. We realized that if we use just one weight per value for images, it's not very smart, because we are omitting the information on the neighbors of every pixel. most likely are related, and it's also not very efficient. So if we represent weights as a matrix, we can actually convolve a filter through the input image and then get new features, the same as I was doing in my software, but instead of predefining the filters, now they're going to be calculated on the fly. Okay, and we're also interested on looking at the images and extracting features from different scales. So for that, we do this pooling operation, which is a subsampling operation. Basically, if we have, for example, this 2x2 image, we end up by doing pooling with a 4x4 image, we end up with a 2x2 image, right? So we extract from every 2x2 pixels 1. We take the maximum value, then we are doing a max pooling operation. We can also do average pooling, and then we take the average of this value here. Okay, so this is important because it's the basis of what we call the deep convolutional networks. We basically stack convolutional filters and then subsampling layers. So we go iteratively creating features at different scales until we reach a point where usually everything is so summarized that we just have a vector. Okay, and when we have a vector, we can actually just plug in a typical multi-layer perceptron. The good thing of all of this is that it can be trained what we call end-to-end. We input the image, we get the output that can be, again, a classification error function or a regression error function, and then we, by backpropagating the error, we adjust the filters of all those layers. What happens here is that the training is usually slow. Well, now thanks to GPUs, not that much, okay? But then what we call applying the network, the inference is very fast. And it's also providing a fantastic result because all those filters are specific for the problem. Okay? Actually, this type of networks, they had plenty of applications in my field, in computer vision, for classic problems like semantic segmentation that I explained before, no? Assigning for every pixel a category, doing detection of objects or classification of the objects in the images for single objects or multiple objects, or even doing everything at the same time. And we have networks to do multitask as well. So what happened in bioimage analysis is that, especially we'll see starting in year 2015, 2016, people started to use this for mostly detection, segmentation, and then applications that are more related to microscopy, like image restoration. We can improve the resolution of our images in the Z direction by just training a model to do that, or even simulate what the super resolution microscope is doing from a low resolution image. Everything started more or less in the year 2015 because there was the appearance of the first convolutional network specific for biomedical image segmentation. Actually, it was presented like that. So use a data set that I proposed, but then it's the basis for many works, as we will see. And then it was the first, it was a 2D version. In 2016 was the 3D version that is just changing filters from 2D to 3D. Also in 2015, there was the appearance, and this is something remarkable, of friendly user libraries. Because until then, everybody had to program to code all of this on their own language, and also if you want to use GPUs to work with CUDA or GPU programming languages, which was a nightmare. Now this is so much easier. So this, just to give you a hint of what this unit is, it's actually a network with the shape of a U, so that's why it's called a unit. And the first part is what we call the encoding path, because it's just doing what I mentioned before. It's just convolutions and pooling, convolutions and pooling. So you see that it goes reducing the size of the images or the features, that we call them feature maps here, until it reaches this point that is called a bottleneck, where the data is really synthesized, and then it goes up. Okay, so symmetrically it goes up. In the original paper, not at the same size, but now we use padding. So the input image and the output image is of the same size. Originally, it was created for segmentation, but this is used now for any kind of image-to-image operation. You may think of denoising, super resolution, You can use this for we call style transfer, to move from one domain to another, for many different things. Even the images that we see now very often in the media from that are generated, synthetically generated, and at some point they use something like this. So what do you need if you want to use machine learning in your research? Well, first you need a problem that needs to have to be well defined, right? So if we are doing classification, the number of classes is to be hopefully well determined, and the description cannot be ambiguous. If we are doing cats and dogs classification, we cannot provide data that looks in between, because it's going to fail miserably. If we are working with microscopy data and we're training on data of high quality, we give it to some experts that are going to annotate it hopefully consistently, so they always mark the same thing, both of them. But we cannot then expect good results if we don't provide the same type of data that we used to train. In terms of infrastructure, well, as I said, most usually we need GPUs. Okay. Now there's cloud computing solutions like Google Colab, which is free to some extent. We have Kaggle notebooks, Amazon, or we have DIPC cluster. And we need data. We need data that is annotated. Usually we move in at least some supervised framework. Now we need data that is annotated so we can simulate what we're doing with the human expert annotations with the machine. How much data? So this is a key question. People used to say, no, deep nets, they need large amount of data. Well, they work very well if you have large amounts of annotated data, but there are tricks to improve the results or pre-train your networks even without labels. Or you can also simulate the data that you have or that you're supposed to have with, for example, geometric transformations of the data that you already have. Or you have, let's say, an image that is very large, where you annotated all the cells. Well, instead of passing the whole image to the network, you can cut it in patches and then train the network with the patches. There's plenty of tricks like adding noise, changing colors, brightness, etc. There's full libraries just to do what we call data augmentation. Okay? And this can help a lot to also regularize the model and make it more generalistic, which is what we want. In terms of resources, well, in biomedical image applications or bioimage analysis applications, we have tools to do annotations, okay, where I'm very related to the ones in ImageJ or PG. Now, the recent studies NAPARI, which is in Python, because most of the deep learning software is now written in Python, mostly in TensorFlow and Keras that belong to Google, or PyTorch that belongs to Facebook, but they are both open source, okay? And the whole community of computer visionaries, let's say, they work with this too. But if you're more related to MATLAB or C, then you have solutions. MATLAB has a nice toolbox for that. If you don't have enough data, there are data repositories, more and more. There's, for example, a competition that is called the Cell Tracking Challenge that has been on for 10 years now. And they accumulated tons of 2D, 3D, and multidimensional data, also in time, etc. You can use to at least pre-train your models. And more, and this is something that I work a lot with, we are creating user-friendly software. So you don't need to know all the basics of deep learning in order to use these approaches. And there's some what we call plugins in ImageJ. But there's also, for example, this nice approach that is used with Google Colab notebooks, where people just have to upload their data and go click, and get the results. And I wanted to present here what we're developing at DIPC, which is the BiaPy library, which also includes this kind of notebooks developed by one of my students. I will introduce it next, but also to facilitate the access to this technology. Since there are so many software, there's actually a big effort, mostly in Europe, on creating what we call a bioimage model zoo. Because of course, if you train your model with different libraries, and then you want to use it from the one that you're more related to, it's not going to work. So we are making a big effort on converging all of these softwares into a single representation of the model, so you can use them in any of them. And there's also examples of state-of-the-art models, results, and data. So just to finish, I want to introduce you a few of the things that we're doing in the lab. As I said, we have one of the big efforts is developed by Danny, who's working here part-time and also as my PhD student. That everything started as actually a master project, and then we started to create things to do semantic segmentation of mitochondria on electron microscopy images. But then we realized that the current solutions were not that friendly, and for us it involved reinventing the wheel over and over. So we created this library in Python where we can create full workflows. So from the input images to the results, or even the analyzed data, to do segmentation of instances, for example, in 2D and 3D, or in more dimensions with more channels, to detection, classification, and we keep adding more and more applications. Another example is what my student Lenka is doing in biophysics. She's working in the interplay between modeling and deep learning, actually with the purpose of modeling the wound healing on Drosophila embryos. No? So we made a cut in the tissue of the embryo, and it usually goes and closes. And what we're doing is using one of the most recent technologies in deep learning to making use of initial set of frames, predict the future. No? Based on the training data, we learn how to produce images. Again, here there's a unit behind to simulate the closure of the wound. Okay? And something that is actually a long effort, but now it's being crystallized by the work of this guy, Ivan Hidalgo, who yesterday presented his master thesis, something that we developed here with some collaborators as well on DIPC, are deep learning methods for super resolution. Okay, so as a microscopy, we use it for cosmological images as well, because actually all those methods are, let's say, agnostic to the data. If you bring an image, then the output, of course, is specialized, but it could be applied to that type of images. And here what we do is that from a low resolution image, based on a scale factor, we produce the high resolution counterpart. Okay? So this can save a lot of time, for example, in microscopy, of acquisition, or damaging the tissue, etc. And here what we did is a big comparison of methods, not just the one that we created last year here, but a set of state-of-the-art methods to see how some of them are more focused on reconstructing the texture of the images or the perceptive quality of the images, and some others are more interested in reducing the average pixel error. So that's it, and just a few take-home messages. I hope it didn't take long, but I try to convince you that machine deep learning is spreading out in the field of bioimage analysis and other fields as well. And it has tons of applications if you have basically images of any type, 2D, 3D, multidimensional videos, etc. And if you want to do classic operations, for that, here with Danny, we have everything ready for you to do classification, detection, tracking, super resolution, etc. There's a few drawbacks that we have to mention. One is generalization, because that's the advantage and the disadvantage of these models, that they are very specialized for the data that you use in general, unless you use very diverse data sets. And then sometimes it happens that you train on some microscopy data, you take data from another microscope that's exactly the same, but then it fails miserably because some particularities of the images that are only seen by the model. Then another one is interpretability. And especially when we work in biological applications or medical applications, this is very important. So even in the European Union, there's a big effort to do what we call interpretable AI. Okay, but this is a field on itself. So there are plenty of methods now to see where the network is paying its attention in order to take decisions. Okay? Because otherwise, we just have a big black box of a non-linear machine that is spitting out results. And another one is computing resources. Okay, because even though we have a very nice cluster here, well, more and more what we see in the media are the results of huge models of billions of parameters that are trained on basically clusters that only NVIDIA, Facebook, or Google may have. And I just didn't want to finish without mentioning applications on beyond bioimage analysis. I let you hear this paper that recently discussed applications on material sciences and ways of adapting the data that you guys have in order to use the models. Do you have an image? Is easy. Okay? For example, for atomic size classification, then you see that they propose something like a unit. But otherwise, there's plenty of things that we can do. You can, for example, represent the structure that you have as a graph, as a vector. You have spectral data, etc. So I think that's it. Thank you very much for your attention. You have questions? I'll be happy.
Okay. Well, before I forget, because I forgot earlier, there will be some pinchos courtesy of the DIPC after the talk. So if you're hungry, stay later. I guess we're gonna meet at the kitchen. Yes. Bye. Okay. I do have a bunch of questions, but maybe you also have some. Well, first question, was the H estimation real or?
No, I have a network. I should use it, but it's actually very good. Actually, the error of these models are now in ±2 years. So it's,
I'm very curious what the network says.
No, it's an inside joke.
Okay, so he was first.
So in the cases of analyzing things such as video data, do you, for instance, take image per image and have a prediction for each of them? Or there's some more sophisticated way in which you include like a time channel or something like that in which you correlate time somehow? Yeah,
so for example, what is the state of the art here is to first encode the information from the video using a 3D network. So you have a 3D encoder and decoder, basically like a 3D unit. Okay, so you keep feeding that, and then in the middle of the network, you get the most synthesized representation of that data, right? So a set of frames. And now this is something that is, I usually tell people that it's like a zip version of your video. And then you feed this into another network. Okay, this is just a vector. It's represented like this, so you see that it doesn't look like anything real. But you feed this vector into another network that is taking the time component into account. Okay, so basically the most successful networks right now are those huge networks are called transformers. Are actually not based on convolutions, but on the original MLPs, and they are used for natural language processing. And in natural language processing, you have a sequence of tons of words. Right? Well, you see, for example, ChatGPT, no? This amazing tool that we have nowadays. Well, in order to produce proper result, you need to keep the attention on things that happen a lot of time before. No, maybe to understand a sentence, you need to keep attention to a word that happened like 30 words away. And these models are very good at that. So they keep the time component that way. So it's basically for sequences. They're really, really good. It's also behind AlphaFold and this type of everything that you can represent as a vector.
Okay, Maya.
Yeah, how many? What's the average number of images or frames do you see you need to train a machine?
It depends so much on the type of problem and I would say the variety of your data. Nowadays, for the things that we do, not that many. With Danny, and the data set that we take, usually with like 20 something images or something like that, we can do a lot of things. Yeah, like thanks to this, there's on the one hand the data augmentation techniques, and on the other hand there's pre-training strategies that they just use unlabeled data. Okay, for example, this part of the network, this is done unsupervisedly. So you just take the input image and you output the input image. But by doing this, going to the lowest representation and then back, then you learn these representations here. And then you can do this with data that is just unlabeled. So you just feed it, and then somehow this encoder learns the structure of your data. There's one approach or one trend nowadays that is called foundational models. That they are trying to create models that are super generalistic, like those that, for example, use in ChatGPT, that then you can fine tune for your specific data with just very few data. Actually, in natural language processing, many people are just doing that because then they cannot train these huge models provided by Google. So they just take them, train, and then fine tune it a little bit with the data that we have.
Marek,
Thank you very much for a very nice talk. I have a question regarding hardware, because you mentioned on several occasions, the computing power you need, GPU and so on. So there are basically on the horizon, let's say, new solution for this kind of application. Like, for example, now people start speaking about like analog computing will be back because it seems to be very interesting for this kind of application. But to what extent this is realistic? You have some in this community, basically, there are some, let's say, new hardware solution for this kind of application.
Actually, that's a very, very big question. So there's, of course, we have to think that there's a big movement in this field because it moves a lot of money. Okay, Google and Facebook, like the media, it's very important, right? So on the one hand, there are approaches to try to use these models in what we call low resource devices, like your mobile phone or a system, security system at home that they don't have a big CPU and even less a GPU. But then on the other hand, those models have to be trained somewhere else. So this ChatGPT or these models that generate images that we all have seen, like DALL-E, Stable Diffusion, Midjourney, they're trained on hundreds of GPUs. So yeah, I know that there's efforts on that direction. For example, for computers that are, how do you call them? Nano computing and quantum computing. Yeah, but I have to say I have no idea in that direction.
one small comment to this question. One of the platforms that are growing decently fast these days is photonics for developing this sort of artificial neural networks, but in an analog fashion where you don't compute anything, but the structure itself computes. Nevertheless, what I want to mention is that this July, or I don't know, I can check the dates later, but we're organizing a conference at the DIPC on that topic, artificial intelligence for photonics and photonics for artificial intelligence. And so, I don't know, we will make the announcement soon. With this little advertising moment, Mika, you had a question.
Just how sensitive are the results with very the structure of the neural network? For example, if you use UNet, you change the kernel of the
Yeah, so that's a big question, especially for someone like me that work in the interplay between computer vision and biomedical applications. Because sometimes if I want to publish in computer science journals, I need to publish a new network. I cannot just take something that is already there and reuse it, unless I invented a new way of pre-training it or using the data, etc. So nowadays, I would say that I wouldn't spend any second on changing model. There are plenty of models that are very robust for 2D, 3D images, sequences, etc. But I think that's something that most of the people or researchers in the field do, is that they spend more time on the data, on cleaning the data, preparing the data, and just applying it later, and see how the way you treat the data or present the data to the model affects the results. For me, it's always a much better solution. And changing the architecture, you could spend years without well, maybe earning 0.1% of performance. That is maybe not significant, because that I didn't mention, but in the GPUs, there's some randomness. Even if you set all the seeds on your code to make it reproducible, but then there's some, how do you call it? I don't know, there's a source of randomness that you apply the same, not apply, but you train the model twice exactly with the same platform, the same configuration and everything. You won't get exactly the same result. Slightly different. So it's not even worth it.
I'm gonna use the fact that I'm the chairman to ask myself a question, because there are too many questions. So it's a question that I had for a very long time, which is that, I mean, we know that convolutional neural networks are amazing, basically, because they work incredibly well. But when I studied them, I could not understand why they should be better than traditional neural networks. So at the end of the day, when you apply a convolution operation, you're losing information. So you have more information before than the one that you have in the next layer. No? And so I never understood why the idea should work in a conceptual, let's say, stage. Do you know why? Or am I misunderstanding something very basic?
Yeah, well, I tried to explain that there was well, first is a problem of number of parameters. You try to do a multi-layer perceptron for an image like this. For every pixel, there are tons of connections pixel to pixel, and then it just explodes. Then, well, if you use filters, you implicitly are including the information of the neighbors of every pixel. No? So you have the picture of a cat, then all the pixels, if you know that this pixel belongs to a cat, most likely the neighbors also belong to a cat. And that information is missed if you just put everything on a single vector. Okay. And this happens a lot. So when you do the convolutional network like this at different scales and different filters, actually there's nice papers about it. You see how the filters that they create, they look at different aspects of the image. And sometimes at the beginning they may be focusing on detecting borders or small textures, but while you reduce the size of the feature map, and but you keep the filter size of the convolutions, in practical terms, you're increasing the field of view of the network at that point. Okay, so then, for example, there's a typical example where you see facial images, and then at the beginning they focus on just edges, textures, etc., and then you start to see the outputs of the filters are pieces of the image, like an eye, a nose, etc., and then at the end you see the representation of the whole face.
I mean, but still, my question remains. I'm thinking more about the guy who developed it for the very first time. What made him think that this idea would be better than any other idea? So
I think it was the fact that you use filters, and they're going to be trained specifically for your problem.
Yeah.
Because we were using filters in a predefined manner before.
Yeah.
Okay. Now these big models, they don't use convolutions. Okay, they're good for some things and not for some others. Like these big,
which big models?
Transformers. They're called transformers. They're the ones that they use after this encoding decoding. You pass that code to this big transformer. Now, this GPT, the T stands for a transformer. Okay. and they have this property of maintaining the attention to you input an image. They have attention in many parts of the image. For example, it's very sparse. You do it in a convolutional network. You can plot a heat map, and then you will see like specific regions of the images that are plotted. And then when you go down, then the field of view, well, the borders, for example, they suffer from this.
Okay. So I don't know, maybe these last two questions and we finish. So Raúl was first and then you.
So I was wondering if you are going to apply all this machine learning approach to science, we will be more and more concerned about quantifying the accuracy and uncertainty attached to this network. So I know that there's this variation in neural networks, but I guess given these areas, I guess it's not so much the focus of Google or Facebook, may not receive so much attention. And I wanted to know your opinion on what is the progress and the future on the error quantification.
Yeah, I'm totally into that. There are ways of providing, for example, uncertainty values or confidence intervals by applying the network several times to different set of your own data. I can send you the way of doing it, but it has to be said that most people don't do it. And for me, it's something terrible, especially with this fight of for publications, because sometimes they give you this model, they claim it's new, they compare themselves to the state of the art, but of course they give you one instance of a model that they train on a specific way, and then it provided good result. They give you the model and the weights, but then you retrain that for your data. It's maybe better to go and use a classic network like the unit that it was already done before. Okay. So for me, it's very interesting to go into that direction and study these intervals. What we do, for example, with my students is that we repeat the experiments. We have time, and we're not so worried about CO2 10 times, and then we provide the average performance plus the standard deviation, especially when we compare each other with other methods, and then we see in which ranges. I think it's more. This is a fair comparison. Otherwise,
so very nice talk, Nacho. I really like it. So in science, sometimes we are much more interested in actually why rather than what. Can we use this kind of, let's say, techniques to learn how the process, to learn how it learns? So for instance, let's say I want to know if a molecule is superconducting. Maybe I'm more interested in why is it superconducting rather than if it is superconducting. Can I extract this kind of information from this kind of models? Or
so that's another rising field, which is explainable AI.
Mm-hmm.
Yeah, and there are. I mean, I'm not into that. I use some of the tools that they provide to, as I said, to understand why it takes the decisions. We have a paper now that we are submitting with some super resolution images, and then suddenly it was detecting some pre-leukemic condition very fast, and with that in the eye we couldn't see it. Right? So what is paying it attention? No? And then what we did is, for example, something quite mechanic could be we work with images, is to occlude parts of the images. Iteratively, you pass the network with by masking some parts of the images, and then you see how the result changes. So you see which parts of the images are more important for your model in order to take the decision. And then you get this heat map of where the model is paying attention. And we discovered, for example, that in the nucleolus, there's some regions that are apparently decisive for the decision. But yeah, as I said, a whole new field.
Okay. Well, just to correct what I said earlier, the conference that we are organizing is from September 2nd to September 6th, just in case anyone is interested. And nothing else. So we have pinchos waiting. Let's all thank Nacho for this amazing talk. Yeah. See you.
I think so. It's particularly in response to solutions.
Llevan un montón de fotónicos que son largos,
Discovering a phone. Is there any way to tackle this problem?
Usually these are all problem-driven solutions.
You need the problems first.